again, folks, in 113. Today we're going to be covering section 9.1, which is the beginning of group theory. Okay, if you look at the calendar, today is Thursday, November 4th, so we're covering 9.1. Next week, just bear in mind, we have Veterans Day. So we'll be working in chapter 9 for a couple of weeks. All right, the packet that I have for you consists of these pages. This is an overview diagram that I made a couple of weeks ago. It will introduce these phrases rather than give you a table to fill in. It's a little, I don't want to corrupt your opinion, it's a little new, a little bit alien at first. So it'll take some getting used to. This is something that you already have, right? In theory, if you watched or you have the documents from section 5.4 or 5.5. We had begun talking about properties properly, right? In proper, right? Anyhow, I just reoriented the diagram so that it's this way, and I added some elements to this that pertain to the discussion of group theory. So do print this, even if it seems a little redundant. All right, I've tried to make this so that it relates to the actual topic at hand. Okay, then there are some examples from the book. We're just doing section 9.1 today. And if you prefer, I swiped these definitions and compiled them into a PDF file, right? From your textbook, right? So you don't have to go hunting for it. All right, and I think that's it. Yes. Okay. All right. So if you're following along, to print that, and you can annotate. I'm going to turn this on as always, and it takes 2 clicks. Okay. See how much I have to adjust this. Yeah, it's a bit off. Way off. Okay. Let's see if that helps. That's a bit better, right? I can't keep this in one place because it's in my kitchen. So I hope you'll forgive me for having to make that adjustment every day. Alright, let's talk about this. Right, here I will shrink it so you can see it all at once. There's the whole forest. Alright. But to get to it a little bit more in earnest, let me zoom in a moment. Okay. We're doing section 9.1 today and nothing more, right? And in section 9.1, you'll hear these phrases thrown about. A mathematical system, a group, and then there's a more specific type of group, namely a commutative group, or alternatively abelian. Right? What is a mathematical system? Sorry. Let's zoom in on this. Okay. A mathematical system is essentially this. It's a set, and I'm trying to be funny here the way that I wrote this, in that I took the letters of the word and separated them by commas, because I'm ham, I guess. Anyhow, a mathematical system, which is really the discussion, all right, is firstly a set, and then also an operation that is involved in that, or joined to it, if you will. All right, what you would call at least one binary operation. Binary operation means that there'll be a number here, whatever it is, some operation, let's just say it's addition, for example, and then some other operation that is applied to it. Some other number that is applied via that operation. Okay, what you'll see mainly, at least right away, is that it involves usually addition or multiplication. All right, just one or the other. Okay, so we're talking about mathematical systems. You have a set of elements, some stuff compiled into a roster, and then either addition or multiplication. for all intents and purposes. All right? Slightly more specific than that situation, a mathematical system, is a group. All right? That's from here on down. If the mathematical system meets these four criteria, that it is closed under the operation, all right? And that has to do with closure. That was from one of those properties that we discussed from last time, all right? Meaning, for example, if adding, you only get more of the same. Type of numbers. Remember, natural numbers are specifically numbers that are whole numbers, but they begin at 1 rather than 0. Right? If you're talking about natural numbers. All right? So if you have the set of natural numbers and then you apply addition to it as the binary operation, right? If you just adding any pair that you could pair together. If it only produces more of the same type of number, namely natural numbers, then it's closed under the operation. It isn't producing something peculiar. All right? If it meets that criteria and these additional 3 here includes an identity element, which is usually the number 1 or the number 0. Has inverses for each element. Remember, there are, if you're talking about addition, there's additive inverses. And then there is, in the case of multiplication, multiplicative inverses, which are essentially fractions. If additive inverses are usually just things that happen to have a negative, opposite, they're the same magnitude but opposite sign, and multiplicative inverses tend to be basically fractions. If those are included in the original set, then we're passing this criterion as well. And then if they're associative, right? Remember, associative is that property where you have 3 elements and you strategically choose to group maybe these 2 together before you add the last, or these 2 together before you add the last, right? If every scenario involving every combination, all right, is associative, right, then your mathematical system qualifies as a group per se. It's a lot to swallow, I admit. Right? If your group then meets a 5th criterion, which is that it is, in addition to being associative, happens to be commutative as well, and remember, commutative property is when you're adding 2 things or multiplying 2 things. If every possible combination of the elements of a set prove to be commutative, then you have an abelian group, right? Just a little bit more specific, okay? So for right now, all that you really need to acquaint yourself with is that there's this idea of a mathematical system, a pile of numbers and an operation, and that if they qualify, all right, if they meet these strict 4 criteria, all right, they might be a group per se. And if they meet a 5th criterion, then they might be an abelian group. Okay? All right, now let me give you something of an overview of what we're going to do over the course of these 3 classes. Alright, this doesn't really warrant a handout that I would give you as a PDF. For us, Chapter 9 will consist of these sections. Section 9.1, which is what we're doing today, Section 9.2, which we'll be doing on Monday, and then Section 9.3, which we'll be doing on the following Monday because we have Veterans Day in between. Right? 9.1, where we are now, right, is an introduction to mathematical systems. Okay? And the type that we're concerned with are the type that are infinite. When we get to section 9.2, we're going to be talking about mathematical systems that are finite, meaning that the sets are finite. These are infinite sets, and these will be finite sets. All right. Now the thing about this is that there are tables that we have to learn to read and other little tricks. All right. We're not there yet. We have to get through what we have to get through today. All right, but eventually what we'll have when we have these finite sets is that we'll be able to compile the elements into a table and whatever the sums or products or what have you would be. Right? So it's only really possible when things are finite to make a table. Right? Otherwise you'd have an infinitely stretching table, and that's, futile. Okay? What we'll be doing in section 9.3 eventually is something called modular arithmetic. And modular arithmetic is basically cyclical. Right? Meaning like a clock is cyclical, it repeats. Right? And there are some notations that we have to familiarize. Right? Now again, I'm not looking to corrupt your opinion, but as you can see, this is kind of weird, for lack of a nicer expression. It's not the kind of thing that you will probably even do with a little kid. So, I mean, if you're going into elementary education, even if you're going into high school education for math, right, this is not the kind of thing that comes up, right? Nonetheless, it's a mental exercise, and that's what makes it worthwhile. Right? So, for right now, there's the plan, right, for the next 3 classes, including today, and here's where we are specifically, right? An introduction to mathematical systems. A set and some operations, right? Infinite sets. All right. All right. We'll take a look at those operations once again. Oh boy, I'm out of the camera really badly, I'm sorry. I don't know why I thought that was a good idea. There you go. Sorry about that. Alright. Here are those properties that we had gone into recently. I reoriented it so that it was a landscape rather than a portrait diagram. But it's the same information largely, and now I've included things that pertain to group theory. All right, so here's a quick review. We have useful properties of mathematics, right? What is associative, and I'll zoom in on this to make it a little bit easier to read. What is important about commutative property and associative property, is that they're basically illustrating the same concept, just in different ways, that the order doesn't matter if you are only adding or if you are only multiplying, right? It's written sideways, but you could have the commutative property of addition, right? Or you could have it of multiplication. It might be a little bit better to back it off now. Right? And as you can see, the whole thing, it looks like it's basically visible. I'm going to close my door over here because I think there's too much light. Dracula needs sunlight. Okay. The associative property similarly has an associative property of addition, notice the pluses here, or multiplication, right? And again, that's an exercise in how you group things, right? For the sake of ideally convenience, especially as a little kid and you're learning your arithmetic, or if you're teaching little kids, right? The point of this is to show them that you don't have to merely accept things as they're given to you. If you see that there is a convenience to add things first or to multiply certain things first, legally speaking, you can, all right? And you would just choose to group those things, hence the parentheses, all right? Then there's the distributive property, all right? There's the distributive property over addition, all right? And as you can see, I'm sorry that this much of it is portrait, but you have this from last class. If you want to eliminate, essentially, a group of things, because you can't actually add or add them or in theory subtract them, then what you could do is distribute the outside content via multiplication to each of the inside contents, and this is the symbolic way of writing that: AB times AC times, right? If in theory you have distributive property over subtraction, this would be the same thing, all right? Just involving minus here and here, all right? What's probably going to be more relevant now than distributive property is these identities to bear in mind, all right? These are relevant to group theory, which is again why I'm bringing them up again, okay? There is the identity property of addition, which involves 0, right? And there is the identity property of multiplication, which involves 1. As you can see, they both basically preserve the identity of the original element. To add 0 to an element, all right, gives you the same element. To multiply by 1 an element gives you the same element. All right? It's that preserving the identity of the original thing. All right? Then there are inverses, right? The additive inverses and the multiplicative inverses. When you have an additive inverse, it's basically the same magnitude number employing an opposite sign. Right? If you're talking about a multiplicative inverse, then you are multiplying by the reciprocal of whatever you have. Even if you started with, in theory, 2/3, it would just be that thing flipped upside down, 3/2, 3/2. Okay? Now, what's going to be important, again, for our sake, is what is written up in the cloud here and what I put adjacent here. Let me go to the cloud for a moment, the thought balloon. All right? It is useful to remember, is that visible? I think it is, but let me just zoom a little bit. All right? It is useful to remember that 0 is the identity element when you are dealing with an operation of addition, right? And 1 is the appropriate identity element when you are dealing with multiplication, okay? Those things have to be included, all right, when we are comparing a mathematical system to these 4 criteria, all right? Sorry, this is getting blurry. These include an identity element. Again, if you're speaking about addition specifically, you want 0 to be included. All right, if you're speaking about multiplication, you want 1 to be included. And if those things do not show up in your set, immediately you don't have a group. All right? It's a way of eliminating that as a possibility. Pretty quickly. Fairly quickly. All right. Now, another interesting thing, which I put down here adjacent, is this. This is a formula that you might want to keep on hand. All right? If you have an identity element, whether it is the number 1 or the number 0, right, what should happen is that any element you take plus or multiplied by that, whatever the appropriate operation is involved, the inverse will produce that identity element. Right. So for example, if the identity element is 0 and the element that you're working with as part of the set is, say, the number 5, right, then already I could tell you you'd have to have addition involved in here, right? Because 0 is the identity element you're going to tack on to associate with addition specifically, right? What would the inverse have to be to make this statement true? It would have to be the additive inverse, this situation that you see here, perpendicular. So the same magnitude, but it would have to be negative. Okay? This is a way of identifying what the inverses would be, and then what to look for in the set to make sure that they're present. All right? Okay. Lastly, before I change the slide here, look over again at this corner. Sorry to make you dizzy. Closure, just to remind you, is the property of groups. It occurs when an operation performed on any two elements of the set results only in another element, meaning more of the same thing, more of the same type of number, whatever that number is, natural numbers, whole numbers, integers. Okay? If closure is maybe the most alien of these, again, not to corrupt your opinion, but in my opinion, all right, it's the most alien because it's you don't use it too often, all right, but it's the first criteria, all right, first criterion, singular, all right, of the 4 criteria, all right, and it might be the little most confusing because it's the most verbose in describing it, all right. When the operation only results in producing more of the same type of thing, then you have closure. Right? I want closure. Sounds like a TV show, right? All right. Now, let's do some examples. And that may be it. There's not a lot to this. Section 9.2 is a little bit more deep. I saw something yesterday when I was printing my papers. Bear with me. No. Now I'm going to save that for when we get to tables. Okay, so let's do some examples to get you through this. All right. I'm going to be stealing. I'll turn this off now. These questions from the textbook examples I have as a PDF for you. That was weird. Okay. So let me just pull that up again. And I'll lighten up a moment here. If you look at example 1 from the packet, there is the solution. I made sure to include that in case you're just reading this, but I'm going to be doing this problem. All right. So in the case of example 1, you're asked essentially, is this a group? I'm paraphrasing here. And the conditions that you're given is the set of whole numbers, to abbreviate. All right, under the operation of addition. We would have to verify with the four criteria. All right. So let's do this as a preliminary step. I have to try to organize myself if I can help it. So when I do these, I write everything down, and I think that's a good habit. We'll do our scratch work here. All right. We're going to be checking these four criteria. All right. We have to make sure that it's closed. We have to see if there's the appropriate identity element. We have to see that there are inverses, all right, for each. All right, and then we have to, in theory, check to see if something is associative. All right, which normally what happens, you'll notice in these instructions, especially if you're dealing with an infinite set, as in the case of whole numbers, they would be infinite. They'll just simply give that to you. They'll go, yeah, it's associative, don't even worry about it. All right, and they might even go, yeah, it's commutative. Why? Because you can't do all of them. The best that you could do is do a few of them and go, yeah, that seems to be the reasonable. All right, so let's do a couple of things, right? Let's figure out, what does the set look like, right, to begin with. If we're talking about the whole numbers, remember the whole numbers are different from the natural numbers because they start with where? 0. Neighbor came home. All right, and we're going to have to include these ellipses because this is infinite. Okay, that's basically what it looks like: 0, 1, 2, 3, 4, and so forth into infinity. Right, and the operation here would involve addition somehow. Right. So, if the system is in fact closed, then the question is, does adding result only in more of the same type of number? Since we're dealing with addition because it's required of us, right? The question of closure is then rephrased. Does addition or adding result only in producing more of the same type? In other words, if you added any combination of two of these, would you end up with more whole numbers? You could try a few, but the fact of the matter is, yes, right? 0 plus 1 is just 1, right? 1 plus 2 is just 3. 2 plus 5 is 7, right? There's no decimals as a result of this operation. There are no fractions as a result of adding whole numbers either, all right? And since there are no integers involved in here, all right, in the classic sense of a negative, I mean, right, you're not going to end up having to worrying about that at all. So, is it safe to say that there is closure here? Yes. All right. Now, the next thing is the appropriate identity element included in this particular set? Right. The identity element for addition is 0, right? Is 0 included in the set of whole numbers specifically? The answer to that is yes, it absolutely does include that. Right. Now, the last thing, which is probably going to be going to upset the apple cart here, is, are there inverses for each of these? All right. Remember, additive inverses are the same magnitude as these, but with opposite signs, essentially. All right. Do you see any negatives involved in this at all? Right? The one exception would be 0 here, right? There are no negatives, right? None of them. All right. So this is where we basically the house of cards collapses. Right? And we would say no. Right? There are not inverses for each of these elements at all, really. All right. So I guess maybe 0 technically, right? I don't have to think about that. Anyhow, it fails to have 1 for every other example. There's no -1 to pair with this in addition to produce 0. There's no -2 to pair with this to produce via addition 0. There's no -3, no -4, no -5, nothing, right? So this fails at the third criterion, right? We don't even have to check the associative property, right? So it is safe to say, in answer to this question, is this a group? You would say no, right? This is not a group. Not, okay? And then move on with your life, right? Not a group. Okay, not too bad, right? Just need to know the criteria. All right, let's look at number 2 from this packet. All right. All right, let me erase a little bit. Okay. Example 2 is again the same question but different conditions that are given to you. So is this a group? What is the group? The set, first of all. The set of rational numbers. Right, and under the operation of multiplication. Now again, because they're just specifying rational numbers, this is another situation where we're dealing with something that is infinite. Right, so in theory, we really can't do everything, but we could check a few things. As if we get to the point where we're checking the associative property, we'll do a few. All right. Let's again begin with how things actually look, though. All right, so what would the set of rational numbers look like? Well, this is a little bit harder to illustrate, but all right, remember, what makes something rational is anything that can be a fraction. So we would need to incorporate fractions. All right, so it would be all fractions, all right, whether they're repeating or terminating. All right, the negatives, 0, and the positives. All right. I don't have the diagram handy, but let me see if I can dig for it, just to point to it. When you're if you're concerned at all about defining what it means to be rational, there is a useful picture here. All right, I'll just flash this really quickly. All right, here's from your book. Everything that is encapsulated under this sort of pink or purple box is a real number, but slightly more specifically are the rational numbers and then the irrational numbers. Because it would seem that there are fewer distinct examples of these, all right, as long as you don't have square roots, all right, famous numbers like pi, all right, you're probably in a safe situation. Now, what are the things that are rational? Anything that can be a fraction, right, is essentially what is rational. Anything that can't be a fraction is irrational. What is rational? If you see here, positive 1/4, negative 3/5, I believe that is, I'm reading it upside down, 7.8, all right, negative decimals, negative mixed numbers, improper fractions, all right, so that includes everything that is buried within this too, all right, so you could take something like even the number 0 and make it rational by sticking a 1 under it. Right? You could take a positive that is even a whole number and make it rational by sticking a 1 under it. I'm sorry, I'm looking for the back of my book here. All right, so let's go through this. It's very sloppily written. So, I mean it, repeaters or terminating decimals, but just for the sake of clarity, let me rewrite that. All right. That's basically the most concise way to illustrate rational numbers, to verbally talk about them. All right, so the question of closure now becomes, does, in this case, multiplying result only in more of the same type of number? Right. You could test a few. Right. I'm a little short on space here, so I hate doing it, but I'll erase this. Right. If you started to take some fractions or anything, and multiply them by something maybe slightly different, all right? Here's a negative integer, all right, which would be included. And here's a fraction. Would you end up with basically something that falls into the rational persuasion? And the answer to that is yes. Because even regardless of the fact that this is an improper fraction and one that has a negative attached to it, it's still under the umbrella of being rational. All right. Test a few, all right, and you'll see that you keep consistently getting the same type of thing in general, rational numbers, right? If it makes it a little bit easier to kind of think about the other situation, namely the irrational situation, when you combine rational numbers with each other via multiplication, they're not going to produce something that's going to be irrational. If it makes it easier to think about it that way, right, you're not going to get any random square roots from multiplying these types of numbers. Okay. All right, so we meet the first criterion. It is in fact closed. All right. Now we have to check to see if there's the appropriate identity element. If we're talking about multiplication, in this case, the operation of multiplication, the appropriate identity element for multiplication is the number 1. And it does include that because 1 is a rational number. It may not look it, right? But if you wanted to write 1 in the style of a fraction, you could put a 1 under it, right? And it doesn't change the value of the original thing, right? This is not a different value than the original thing. Right? Now, the question of inverses for each. Well, when you're dealing with a whole number, we need to, in this case, we need to consider, because we're dealing with multiplication again, the operation of multiplication, we need multiplicative inverses to be present, not to be president. Don't vote for them. Multiplicative inverses are reciprocals, generally speaking, right? So if we had, say, -5, right? The multiplicative inverse would be the reciprocal of -5. What would be the reciprocal of just 5 in general? Well, it would be this, if you can imagine it having a denominator of 1. Here's a phantom 1 here. It would just be this flipped upside down, right? When it comes to multiplicative inverses, we're not really concerned with the sign, so you would just assume that it is exactly the same sign here, right? What should the multiplicative inverse produce, right, in theory, when you combined it with the original figure? Here's this formula down here. You take an element, and in this case we're multiplying it because that was the given operation, and we're multiplying by its inverse. What should it produce in the case of multiplication? Well, if the identity element for multiplication is 1, then in theory when you multiply these things, you should ultimately get positive 1. Right. So let's see if we do. Right. -5 times -1 is positive 5. Phantom 1 times 5 here would be just 5 again, and that does indeed produce 1. Right? That's just one example, but you would try a couple at least. All right, look for some kind of special cases. All right, the real question is this something, this -1/5, that in theory would appear in the set of rational numbers in general? It would be, because it's a fraction regardless of whether it is a negative or not. It's under the umbrella of being rational generally, right? It's not under the umbrella of being integers specifically. So -1/5 is totally cool, right? Now we might get into some trouble when we consider the one interesting case that's part of this set of rational numbers. Right? If this is true, this formula, that an element, in this case times its inverse, should produce 1, what would happen if we incorporated 0 here? Zero is, first of all, an element of this set, because even 0 is considered rational. How come? Because 0 you could just stick a 1 under it, all right, and it is disguised as a fraction, essentially. Now, if we use the element of 0, is there actually anything times 0 that would produce the appropriate identity element in this case, which would just be the number 1? By definition, the 0 property of multiplication, right, what are you going to get as an outcome instead of 1? Right? There isn't anything that we could conceive of that is going to satiate this situation. Right? Put a circle around this little formula at the bottom here, right? I wrote it sort of backwards, but it doesn't matter. If you know what the identity element is, we know that in this case it's 1, that when you test it with any of the elements, in this case you're testing it with 0, you can always ask yourself the question, well, what is it times 0 that in theory would produce that thing? And then ultimately when confronted with the question, you go, there isn't anything, all right? So if there isn't anything logically, then unfortunately we're failing in this situation. There are not inverses for each of these because we found the one instance where it doesn't happen. Right? So there's no point in actually checking the associative property. This is again an example where you would say that this is not a group. Not a group. Okay, example 2. Let's do the last one and then we'll stop. I believe this example asks us to go the whole 9 yards and check the 5th criterion. So let me see. If you look at example 3 from the set in the packet here, dexterity. If you look at example 3 in this packet, we're checking here. It seems that we're going to be going the whole 9 yards to see if this is commutative as well. All right. It's a little sloppy. Sorry for the mess. Is that legible? I think it mostly is. All right. For example 3, is this an abelian group? Or what you might say is a commutative group. What specifically is this, all right? The set of just real numbers, right? And the operation is under addition. All right, so again, we'll have to sort of modify the question about closure to adapt it to the scenario described, right? All right. Does adding real numbers result only in more of the same type? It might be good to sort of draw a picture of what real numbers would look like, but because it is more general, the most general, all right, I'm going to refer to again this diagram from a while back, all right, from last time, because it's a good summary. All right. Here you go again. All right. Everything that is in this box, including the irrational numbers now, are real. All right. We don't have to worry about imaginary numbers at all. All right. But this is quite a vast array of different things. All right. Fractions, even fractions with a negative sign. All right. The number 0 itself, any of the whole numbers, any of the integers that are negative. All right. And pi even. All right. So a lot to go through here. What are the real numbers essentially? To summarize, everything but the square root of a negative. Since the set of real numbers is excluding that, at least that one situation, right? Does adding real numbers result only in more of the same? Yes, because, you know, remember, even pi, though it is infinitely stretching, it's still under the umbrella of a real number, all right? And if you added something to it, all right, even if it was a, you know, a terminating number like 1, all right, and make it 4.14159 into infinity, it's still a real number. It's not a negative square root. So adding real numbers results only in more of the same real numbers, right? You're not getting a negative square root by any process of addition, right? So is it closed under the operation? Yes, most certainly, right? Is the appropriate identity element for addition included in the set of real numbers? Remember, for addition, 0 would be the appropriate identity element, all right, and it is in fact a real number, so yes, it would be in that set, right? Are the inverses available for each of them, all right? If you check a few, all right, it would be good, all right? Remember this formula again. An element, in this case we're talking about addition, plus its inverse should result in the appropriate identity element. Okay, so since we're talking about addition, I don't know who that is. Since we're talking about addition, right, the appropriate identity element we have decided is 0. All right, we could test a few elements, try to conceive of their inverses and see if we end up with 0. If we do consistently, all right, we're good to go. If you want, you could actually rearrange this, right? If you have a little bit of trouble identifying what this is, exactly the inverses that ought to be there, right? You could rearrange this algebraically in theory, right? The inverse would be equal to the identity element, right? Minus, because we're putting this on the opposite side, because we're talking about addition here, an element. So if the identity element is 0 and you have the operation, pardon me, you have the element, say something like 2, that would have to be the inverse, the outcome of this. 0 minus 2 would be negative 2, right? Positive 2 plus negative 2 would produce a 0. That's just the whole numbers granted, all right, but that qualifies here. You want to try something more sophisticated, all right? We can. So let's say that you had pi, right? Because that's the kind of the most interesting irrational number for right now. All right. If I have the element, I'll put this in green. That is an example of an irrational real number plus its inverse. Does that produce 0? All right, I'm looking at it from this perspective. Well, if the element is pi, which as you know is 3.14159, whatever many decimals you like, all right, what combined with pi would cancel it out entirely, all right, and produce 0 as the identity element? It would, in theory, as silly as it may sound, it would be negative pi, right? Is negative pi feasible? All right, it's not listed in the diagram, but it certainly is, right? It would be the inverse of this, right? Then there's the situation of 0 itself, right? That might sound a little goofy, right? But let's say that the identity element, let's say that the element that we're adding or subtracting, we're adding in this case, to produce 0 is 0 itself, because 0 is an element of real numbers, all right? What is it plus 0 that would give you 0, all right? 0 itself, all right? That's interesting because what that means is that 0 is its own inverse. Interesting, right? Anyhow, no matter what you do, right, what's going to happen is that, yes, we're going to qualify as all of the inverses of real numbers are there. You're not producing any imaginary numbers, right? They don't usually bring up the subject of imaginary numbers when you're talking to little kids, right? As a matter of fact, it may not even come up in high school unless you see algebra, maybe algebra 2 even. You have to sort of at least be aware that something exists. So I'm kind of glad that I gave you that diagram a while back. All right. Anyhow, we do, in theory, have to check at least a few of these, right? There are properties, right, of real numbers, right? Associative is officially a property of real numbers to begin with. All right, so if you know that, you don't really have to check, all right, as well as commutative is a property of real numbers. They're not talking in this example 3, all right, they're not asking you about anything other than real numbers, so if you know that by definition, then you could spare yourself a little bit of trouble. If you want, I mean, it is worth exploration, so try a few combinations. All right, that's setting a good example for the kids and for yourself, you know. All right, this is the associative property, right, of addition specifically. Associative. It's a bit faint, so hopefully that's visible, right? Try some numbers, all right? All right, you could, if you really want to get into the weeds, you could start trying out, you know, interesting things like the square root of 2 and, you know, pi or whatever, but that's really, that's very adventurous of you, and I wouldn't want to talk you out of it, but let's try something easy like some whole numbers here, all right? These are real numbers, 1, 2, and 3. If I'm using the associative property, they would be sitting in the same positions in the model, but you'd be grouping these instead of these. They have one element in common term. And if you end up adding these first, you get 5, right? And then if you add these, you would get 6. All right. If you add these, you'd get 3 first, and then if you add the outcome, you would also get 6, right? The property illustrates that the order in which you add things, as long as you're just adding, doesn't really matter. All right? That's only one example, but because you're dealing with something infinite, you really can't do all of them anyway. Anyhow, if you test out the commutative property of addition, that's this. A plus B is equal to B plus A. Sorry, it's faint. All right. Substitute in some values. All right. You could again try out something more adventurous, like some irrational numbers. All right. But you should. They're infinitely stretching. Just realize, so you're only going to be able to see the front end of it. You know. Regardless, let's just say this: 3 plus 7 plus 7 and 7 plus 3. Right. Whether you arrange them this way or this way, you're going to get the same sum. Right. What is the point of commutative property? Well, similar to associative property. The order in which you do things, as long as you're just adding, or in theory, if you're just multiplying, it doesn't matter. You have the freedom to put things in any order that you find convenient, right? Anyhow, without trying in futility to test every possible combination, you could say with certitude, right? Since this is in fact a property of real numbers, and this is also a property of real numbers, and real numbers is the thing under consideration, that is in fact, yes, is the answer to this question. Yes, a commutative group. Okay, and I think that might be it. It'll take a little getting used to, right? Again, when we do section 9.2 on Monday, we'll have tables because we'll be dealing with finite sets rather than infinite sets. All right. So, if I can stress one point again, right? Even if it seems redundant, print this version of properties, all right? Because it has the pertinent information here. Somewhere I should have put that in a balloon too, to be fair. Here and here, insofar as groups are concerned. Okay? It will hopefully give you a leg up. All right. So, what to do? Let me just remind you, as a good habit, all right, for homework, do section 9.1 in MyLab. If my memory serves me. In the case of chapter 9, there is no prerequisite, like chapter 5 had a prerequisite way back, and chapter 2 had a prerequisite. All right. So don't worry about that. Just start on section 9.1. All right. Please, whatever you do, don't make the mistake of waiting too long before you begin this stuff, because it is, kind of alien. All right? You don't want to wait until the end. All right. That's it for today. Thank you guys for sticking with me, and I'll see you again on Tuesday. All right. Be careful out there.